So we have the stationary process and Markov assumption. Okay. So with the set of state and evidence variables for given problem that decided on. Okay. The next step is to specify the dependency among the variables. What is the next step? We have to obtain the dependency among the variables. We have set of states and evidence variables for any given problem. So now we have to obtain what is the dependency among the variables. Okay. So how do you obtain the dependency among the variables here is, first we have to order the variables in natural temporal order depending on the time. Okay, which variable is starting first, that variable will be considered first. Okay, temporal model is based on time. Okay, so the variables will be ordered in the temporal order. So it means that what first, which is the cause that will be affected, cause, cause and effect will be having the, which is the main variable that is giving the cause, that should be considered first. Then the variables which are affected by those variables will be considered next. Okay, so we have to order the add the variables here in the causal order. So whenever we are adding the variables, we have to take the causal order only. Okay. So what is the obstacle here is, the set of variables is unbounded. What is the number of variables we have? We have total number of variables. What is that? The state variables and evidence variables. Set of these variables is unbounded. So we have more number of variables, unbounded number of variables, because it includes the state and evidence variables for every time slice. See here, the state and evidence is changing every time with respect to time, is or no? So if you take blood sugar level of a patient, every time it will be changing. Okay. So whenever we are representing this state and evidence variable for every time slice, if you consider this becomes unbounded. Okay, we have infinite number of values. Okay. So that is the main problem here. Okay. So this problem, this is the set of variables are unbounded. So this problem creates two types of problems. The first one is, we might have to specify unbounded number of conditional probability tables, one for each variable in the each slice. Okay. So in each slice we have the state variables and evidence variables. Okay. So whenever we are writing this Bayesian network, we have to represent conditional probability table for each variable as or no. So how many variables we have? Unbounded number of variables. Since we have unbounded number of variables, then it will also have unbounded number of conditional probability table. This table will have unbounded number of conditional probability. That is one problem. Okay. The second one is, one might involve unbounded number of parents also. So whenever we are ordering the variables, we have discussed that we have to decide the parents of each variable. So here, what is that? Since the variables are unbounded, here it will also have unbounded number of parents. Okay. So how do we solve this here? The first problem is solved by assuming that the change in the world state are caused by the stationary process. Okay, so the world state, that the environment is changing, no? That can be that will be represented by stationary process here. Okay, so that is the process of change that is bound by the laws that do not themselves change over time. Okay. So what is stationary process? Here, the variables are not changing over time. Okay. So the variables do not change themselves over time. Okay, but the change is bound by the laws here. Okay, that is the first step. So given the assumption of stationary, we need to specify conditional distribution only for the variables within this representative time slice. Okay. So what is that we have to do? We will be specifying conditional distribution for variables only in the given time, representative time slot. In the given representative time slot only, we are giving the conditional distributions. Okay. So like this, we will be solving the first problem. So what is that we are doing? We are here, what is that? The change is represented by the loss here. The variables are not changing by themselves here, but the change is represented by the loss. Okay. So because of that, what is that here? The conditional distributions for the variables will be represented within the representative time slot. Okay. In the representative time slice only, we are giving the conditional distributions. Like that, we are solving the first problem. Okay. The second problem, that of holding the potential infinite number of parents. What is the second problem here is that each variable is having infinite number of parents. Okay, so that can be solved by so the second problem, that is holding the potential infinite number of parents, is solved by Markov assumption. Here we are using Markov assumption to solve the second problem. That is, the current state depends only on finite history of previous states. Here, what is that current state depends only on the previous state. Okay. The process satisfying these assumptions are called Markov process or Markov chain. So the current state depends only on the finite history of previous states. This process. The current state is depending on the previous state. Okay, this process is called Markov process or Markov chain. Okay. So this Markov chain or Markov process comes in various methods. The simplest of this is first order Markov process. So what is first order Markov process? In which the current state depends only on the previous state, not on any earlier states. What is first order Markov process is that the current state depends only on the previous state. It does not depend on any early states. Okay, that is the first Markov process. So using the notation, the corresponding conditional independence acceptance states that for all t, how do we represent the p of x of t? Xt is the current state. The xt depends upon the previous states. What are the previous states? X0 to t minus 1. All these previous states. What is first order Markov process? The current state depends upon only the previous state. So this is equal to what? P of xt given x or xt minus 1. Okay. So what is xt minus 1? Is the parent of xt. Xt minus 1 is the parent of xt. So the current state xt depends only on the previous state xt minus 1. Okay. So in general, what is that given? In general, it is given that the current state depends upon all its previous state, history of evidences. Okay. So the current state of the patient depends upon history of evidences. Is that no? So here, instead of taking history of evidences, we are taking only the previous state. So that is called first order Markov process. Okay. So in the first order Markov process, the laws describing how the state evolves over time are contained entirely within the conditional distribution. How the new state, the present state evolves depends upon the previous state. Okay. So the conditional distribution is given like this: P of xt given xt minus 1. Okay. So this way of representation, P of xt given xt minus 1, is called transition model for first order process. Okay. What is this? P of xt given xt minus 1 is called transition model for first order process. Okay. So similarly, the transition model for second order Markov process is, so in the second order, what is that? The present state depends upon the previous two states. Okay. So xt is the present state, students. It depends upon its previous state. T minus 1, T minus 2 are the two previous states. That is why it is called second order. Okay. Second order Markov process is the conditional distribution. It is given as probability of xt given xt minus 2, xt minus 1. Okay. So here the Bayesian network structure corresponding to first order and second order Markov process is given here, students. You see this figure, all of you. What is first order? Xt minus 1 is the present state. It depends upon the previous state. Xt minus 2. Xt depends upon xt minus 1. Okay, like this. This is called first order. The figure A represents first order Markov process. The figure B represents second order Markov process. Okay. So that is the this way of representation. This is called transition model. Okay. So this is the transition model for first order Markov process, and this is the transition model for second order Markov process. Okay. So in addition to restricting the parents of state variable xt, we must restrict the parents of evidence variable et. Okay. So what is that we are doing? We are restricting the parents of the state variable xt. No? So what is that? The xt minus 1 depends upon xt minus 2, like that. It depends upon the previous state. So in the first Markov process, in the second Markov process, xt depends upon its two previous states, xt minus 1, xt minus 2. Okay. So what is that? Here we are restricting the parents of the state variable xt. Instead of restricting the parents of state variable xt, we restrict the parents of evidence variable et. So what is that we are doing here? The evidence variable at time t depends only on the current state. So probability of et given xt minus 1, e0 to t minus 1 depends only on the present state. That is probability of et given xt. So we are restricting the parent of evidence variable. So this P of et given xt is called tensor model. Okay. So this is the figure of the tensor